In this cast, we'll have our first look at scalars and vectors. So scalars are quantities such as distance and speed. They tell you how far or how fast are moving. So how fast is, if you're in a car, you have the speedometer. How far something moves is the odometer. Okay, all of these have just magnitude, meaning they have some kind of value. So these are scalars, and they have only have magnitude, only magnitude. Now, another set of quantities that we have are quantities that have a magnitude and a direction. Okay, and this is what we call vector quantities. So vectors, okay, they have magnitude, and direction. Okay, so for example, velocity is 35 kilometers per hour east. That has the magnitude 35, which is basically a speed, and a direction of east. Okay, these are things that you find on a GPS or when you tell someone directions from a map. Now, vector quantities are graphically represented by arrows. Okay, and the greater the vector quantity, the larger or the longer the arrow, which makes sense. So let's look at a position vector. A position vector points from the origin, okay, to the location of an object. Okay, so let's look at this point A first. The position vector would go from the origin, point all the way up to that point. Okay, so the way we would write this is D, position A, and we have a little hat or a little vector sign on top, which tells us that this is a vector, is equal to 5 meters in square brackets north. Okay, so this here is the vector notation. Now, but because this point A or this vector is on the y-axis, we could also use the 1D notation, which we learned earlier. So it's on the y-axis, so this is the same thing as y is equal to plus 5 meters. Okay, we do not need to put the little arrow on the y because the direction is already implied. Okay, so this is what we call 1D notation. Okay, it's very important. Let's try another one. Point B is right here, and so the position vector would be like that. So in standard notation or vector notation, this is dB with a little hat or vector, and this would be 4 meters west. In 1D notation, well, this vector is on the x-axis, so x is equal to, and because it's west, this would be negative direction, so negative 4 meters. Okay, so again, that's 1D notation. Now, 1D notation doesn't work for vector C because it's not in 1D. So in this case, because it's in 45-degree angle, we're kind of lucky that this is 6.5 meters southwest. Okay, so we can express that vector in that way. We can't use 1D notation here because it's not one dimension. Okay, so moving on to vector D. Okay, here we can't use southwest or northeast because it's not a 45, it's at 23 degrees. So what we would write here is that this vector D is at 7 meters, square bracket, 23 degrees north of east. Okay, we start here and we go 23 degrees up or north from the east axis. This is the same thing, or the same vector could be written as, because 90 minus 23 is 67, so this angle here is 67 degrees. So this could be 7 meters, 67 degrees east of north. Okay, let's try another one. It takes a little bit of time to get at this. So let's try vector E. We have here is 58 degrees, so this would be 9 meters, square bracket, 58 degrees east. We're going east of what axis? The south axis. Okay, so we would say 58 degrees east of south. Or if it's 90 minus 58, this would be the same thing as 32 degrees south of east, because this angle here is 32. Okay, so moving on to, so this is position vectors. from position, if we have change in position, we have a displacement. Okay, so we have to look at a displacement vector. Displacement vectors are drawn from the object's initial position to its final position, regardless of the actual path followed between these 2 points. Super important because we have little roads here in gray. So we have to, let's say we have to travel along these roads. So the distance going from here to here in this red first vector, we would say d is equal to 40 meters. This is a scalar quantity, right? So it's just distance. But displacement tells us how far out of place we went from the initial position. And if we started at 10 and went to 50, this would just say we went 40 meters east. Now, because this is in 1D, we can use the 1D notation, which would be delta x is equal to plus 40 meters. Okay, let's try another one. Let's try the blue vector. So if we start at the position here and we end here, well, if we want to look at the distance, we just can't cross the grass. That wouldn't be good. Let's just say we have to travel around. So this would be 10, 20, 30, 40, 50, 60, 70, 80, 90. Shoot. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So this distance here would be 100 meters. But the displacement vector isn't of length 100 because the displacement vector points from the initial to the final. So the length of the displacement vector, delta d, is equal to 40 meters and points in the south direction. Because this is in the 1D again, we can just say that's delta y is equal to negative 40 meters. Okay, so this is a very good example of how distance is not the same thing, so it doesn't equal displacement. Even though the magnitudes of these two quantities can sometimes be the same, if you don't change direction, the distance will be equal to the magnitude of displacement, but the two quantities are very different, so just be really careful about that. So the last one, probably most challenging at this point, is this green vector here, because we could see that we would travel 40 meters this way, and then we would travel 30 meters this way. So the distance for the green vector, d, would be 70 meters. But displacement is not 70 meters. It's just this length of this vector here. Well, how do we calculate the length of that vector? Well, for that, we can use the Pythagoras theorem. Okay, it's basically the addition of two vectors. So we can have our first displacement vector here, which is 40 meters. And if we put that tip to the tail of this vector, which is 30 meters, okay, this is called tip to tail. This is in vector addition. So vectors are added tip to tail. So this is tip to tail. Okay, we need to find the length of this vector. Well, in order to do that, we need to use either a ruler and a protractor to do this graphically, or we can do this mathematically by using the Pythagorean theorem and trigonometry. Okay, so this green vector, well, it's red now, is called the resultant vector because it's the result of adding the other two vectors. Okay, so to find the resultant, delta d, so this is delta d, that would be equal to, if we use Pythagorean theorem, is 40 squared plus 30 squared, which is equal to 50 meters, and square root of that, because a squared plus b squared is equal to c squared. So we know the length of this vector is 50 meters, but now this is a vector quantity, so we also need to find what this angle is. And so to do that, we use trigonometry. We know that tan theta is equal to opposite over adjacent, which would be 30 meters over 40 meters. And then you need to do inverse tan, and you get an angle of 37 degrees. Okay, therefore the displacement, delta d with a hat, is equal to 50 meters, square bracket, 37 degrees south of east. Okay, so let's have a quick look at a model problem. Okay, so here we go. A hiker heads north and walks in a straight line for 10 kilometers. She then turns left and heads west for another 5 kilometers. What is the hiker's distance and displacement for the trip? Include a vector diagram. Okay, so she walks in a straight line for 10 kilometers. So maybe you have 10 kilometers this way. She walks north, and then she turns left and heads for another 5. So it should be about half the length, about this way. So that's 5 kilometers. Okay. What is the hiker's distance? Well, the distance is 10 plus 5, which is 15 kilometers. But the displacement is the resultant from the initial position to the final position. Okay, so this is the displacement vector. And how do we find that? Well, we need to go displacement is equal to square root of 10 squared plus 5 squared. And that's equal to, if you do this on your calculator, 5 squared plus 10 squared and square root of that. Which is 11.2 kilometers. And now we also need to find this angle. So to find that angle, we know that tan theta is equal to 5 over 10. So half. So you go second inverse tan of 0.5, or 5 over 10. You can put that in your calculator, make sure it's in degrees, and you get about 27 degrees. Okay, so the displacement hat is 11.2 kilometers, 27 degrees. We're going west of the north axis.